Recording is rolling. So welcome to Monday, October 18th. We're starting a new section today. This is going to be an energy section. A bunch of you guys just turned in your centripetal force and gravity quiz. What did you want to say about that? A couple of things. One is that, this number 4 question, I know I did go over this in class, but because this does involve most of the information that we're about to do, like starting today, I think I'm going to throw this out, although I am curious to see how many guys did get this right, but I don't feel super right about grading that. I should never put this question on here. There's an obvious better question I should have put, but that's fine. And one other thing is number 9, centripetal force lab. I said you quadruple the weight, and then I listed that in grams, which is definitely a typo that I didn't catch until this morning, because weight is not measured in grams. Weight is measured in what? I could have said newtons or millinewtons would have been okay, but not grams. So not sure what I'm going to do about that yet, but those are the two, if I could reverse time and pick something, and those would be the things. Also, before I get going too far, Martian night sky. Let me flip my screen over, because I found this animation over the weekend. I was like, oh, this is so cool. I have to show all my students. And so this Mars rover checking out the Martian night sky. That's what it looks like at nighttime on Mars. Now, obviously, you see like way more stars there than you would on Earth. I've been asking students today, like, why is that? And they've given me 2 reasons. One is maybe a stronger reason than the other. Oh, yeah, you were saying.
What's that really, really, really bright one at the top?
Oh, you know what? I do not know what any of these stars are. Let's see if we can see. Oh, interesting. Like in the middle of this. Yeah, actually, that you guys do you see kind of like a stream of stars? It looks like kind of in a line here. You guys know that that's the main part of the Milky Way galaxy, right? And you guys know that light pollution has really only existed significantly since electric lighting has been around for like not much more than 100 years now. So people used to be able to see this Milky Way formation in the sky. Like if you go back like 200 years ago, you could see that. How many of you guys ever been like way out in the middle country, like in the middle of nowhere? You have seen the night sky? Right? Now it doesn't look exactly like that, but it's a little bit closer to that, isn't it? Right? Once you get rid of all that light pollution. That is a good question. What star is that? Like right in the middle? I do not know. But one thing I think is kind of interesting is go back in the day, like before people had lots of distractions. If it's nighttime, what are you going to do? Other than like stare at the sky. People used to be able to like read the sky, navigate the sky, like the same way we can read a book. Right? It's just like, oh yeah, like that constellation's there. Oh, that must be like exactly north, northeast, right, something like that. But what's the main reason besides light pollution, which is also a reason? But what's the main reason other than that the night sky is so clear on Mars compared to Earth? Yeah. Atmosphere. Yeah. Mars has a very thin atmosphere. I forget exactly what it is compared to Earth, but I want to say it's like 1% of what it is on Earth. It's very thin compared to Earth. Yeah. So that's the main reason. All right. So that was fun, but let's get back over. All right. So agenda today. First, I'm going to talk about. There's energy and energy conservation. We've got power as a new variable also on the list, but not going to quite get to that today. Okay. Oh, here's your guys' new assignments. So AP Classroom Unit 4 multiple choice. I opened up over the weekend. So have the due date for that 1 week from now. I'm pretty sure I'll have gone over enough stuff by the end of this week that you guys will be able to do that. If not, we could always postpone, but let's do this for now. Okay? And then I got new puzzles for you guys. Do you guys see a clip to the front of your desk? A page that looks like this. So it's chapter 5. That's got a motorcycle. Okay. Does anybody not have this page? Okay, so you guys got this? Okay. All right, so let's do the same thing we've been doing the last couple of sections that I think's been working out pretty good, which is I give you guys this main homework that I'll go over the problems of some very similar ones in class, and then have this bonus homework that you could also do for bonus points that some of you guys have been taking advantage of, which is really awesome. So there you go. Now these problems are listed on Focus, and these problems are also listed on Google Classroom. So it's all there, and obviously it's here too. being recorded. You know what, if that's not working, then go down to here and you can just manual do it that way. Okay. All right, so you guys good so far? Also, hey, look at this right here. We got Leaning Tower. We got stuff being dropped off Leaning Tower. What's the speed at the bottom? This is a story that keeps coming back over and over in this class, isn't it? So Galileo dropping stuff off Leaning Tower. And the reason I'm throwing this story here is that by the end of today, you guys are going to see that there's actually an alternate way to approach this question of how fast does anything crash land at the bottom of a cliff, bottom of a tower. You guys have a way already. You guys remember if you know some kinematic stuff, say if you drop something, like how fast does it crash landing, you might take advantage of that third kinematic equation and figure out the crash speed. But today I'll show you guys a different method using energy conservation principles. And what you guys will see is that a lot of the problems that you know other methods to solve for already, you guys are going to get this new method, conservation of energy, which leads to the exact same answers. So you'll have now like new tools in your toolkit, new ways to solve things. And sometimes the way that I'm going to show you guys how to solve stuff now is actually a faster, more efficient way to solve it than what you know already. Okay, so you have, you guys will see examples as we do this. And sometimes there'll be setups where actually this is the only good way to do it in a physics one context. So yeah, that's what we're looking at today. All right, guys ready to start this adventure? All right, so we got a bunch more paper out here. Keep it track right. I think I'm gonna need 11 pages of paper today. Something pretty close to that. All right, so energy. This is a new variable in this class. We haven't talked about energy yet. Okay. So energy, a variable, is measured in joules, which is capital J, okay? And joules is the unit. It's the SI unit, the metric unit. Okay? I want you guys to know that energy is a scalar quantity as opposed to a vector quantity. Okay, you guys remember vectors and magnitude and a direction matters, but scalars, it's only the magnitude that matters. So, we're gonna, well, joules, like some number of joules, does not have a direction associated with it. Okay? And by the end of class today, what's gonna be really important is that energy is conserved, meaning that you can't create or destroy energy units. Right? You can transfer energy units though, right? And usually you write energy conservation like this: the sum of initial energy is equal to the sum of final energy within some closed system, something like that. Okay? Get into more details about that later, but just flash this up here now, just so you can think, okay. So if you look at some initial state in a system, some final state in a system, if it's a closed system, there's nothing outside, no outside forces on it, then you can account for the energy and say, like, oh, all the energy at the beginning equals all the energy at the end, and then maybe you could go solve for stuff once you set up equations. Okay? So that's going to come back. Now, back to this idea of joules for the unit. What is 1 joule? 1 joule, what does that break down into? That's the same thing as 1 Newton meter, okay, which is about to make sense when I give you guys the formula for work. Okay. And 1 Newton, you guys remember, is also a composite unit. So joules is a composite unit, Newton is a composite unit. Newton is what does 1 Newton break down into? Kilogram meter per second squared. Exactly, yeah. Because you guys remember Newton's second law of motion, F equals ma? Force, Newton, ma. Kilogram meter per second squared. Okay, so that's that, right? And then if you put it all together, then 1 joule of energy, in terms of fundamental units, you guys remember first couple weeks of class I told you there were like 7 fundamental ways to fundamentally measure things. Okay. Got kilograms for mass, meters for displacement, time, seconds for time, the other ones. Okay. It's like this: 1 kilogram meter squared per second squared. Okay, so here, keeping real close to track of what that means, what's going on. Right. When you pump a gallon of gasoline in your car, there's some stored energy that's associated with that gallon of gasoline that'll move the car so far. If you wanted to, you could quantify it in some number of kilogram meters squared per second squared. Or if you've been running a laptop computer for an hour, right, there's some energy that was associated with that you could quantify in like this. Okay? There was some power plant on the other end of the electric grid that had to supply that energy in terms of kilogram meters squared per second squared. When you, if you ate breakfast or lunch today, then there's some energy stored in that food that's usually quantified in calories, like on nutrition label calories. What 1 calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. And then food calories, so it's technically kilocalories, so it's a factor of 1,000 of that. But you could convert calories to joules or vice versa, but we care about joules because it breaks down into this. Okay. Right, now, the next few pages of notes, I'm going to give you guys what I call building blocks of energy. Really, I should say mechanical energy. Now, building blocks is my sort of like Griffin colloquialism. It's like nobody says that, but mechanical energy, this is a term that AP uses, right? Because energy can take many forms, but there's only a handful of forms that we're going to care about for this class that we're going to use to set up conservation of energy equations. Okay. Now, this first one is maybe not technically part of the set, but we'll treat it as part of the set. It's going to work out. Okay. So it's called work. Okay. Now, work is, again, not technically a form of energy, but it's a transfer of energy. Transfer of energy. Okay. Because remember, you're allowed to like transfer energy from one system to another system, from one object to another object. That's okay. We'll talk about gravitational potential energy. Talk about energy stored in a spring, which is called spring potential energy. And then we'll talk about energy of motion, which is called kinetic energy. Okay. So that's sort of the shorthand version of the list of building blocks that we're going to care about. Okay. Now, does energy take forms other than just these four? Yeah, definitely. So I'm leaving a bunch of stuff off the list. I don't have nuclear energy up there. I don't have thermal energy. So yeah, I don't have chemical energy, like energy stored in a AA battery. Okay, so there's lots that are left off, but we'll be able to use these and then take whatever we want out of those. Okay. Okay. I'll start with that first one, work, transfer of energy. So work, transfer of energy. Work is equal to force times distance, but there's a particular way that I'm writing this. Do you guys see that big old dot between the F and the D? Okay, so F stands for force, D stands, well, maybe I should say displacement. Okay, so if you push or pull on something, and as a result you move it so far, then you've transferred some energy into it as a result. Okay. How much energy? Well, force times distance. Okay. That's how much work you've done on it. That's how much energy you transferred. Okay. Now, what's the deal with this big old dot? Okay. Well, this is called a dot product. Dot product multiplication. Okay. So, and what that means is that well, think about it before I tell you exactly what it means. Think about what are some things it could possibly mean. Okay? I mean, force, that's a vector quantity, has magnitude and a direction. Displacement, also magnitude and direction. But like energy, I told you was a scalar quantity. So there are different ways to multiply vector quantities together. There's different things that could possibly mean. Okay? A dot product is in contrast to what's called a cross product. That is going to be important later, but not today. So what a dot product means is that you only multiply together parallel components. Okay? So if you're pushing on something and it moves some displacement, you only care about the parallel parts, and I'll draw a picture for you guys in a minute so this makes sense. Okay. And sometimes it's written this way: work is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Okay. That's also a way to write dot product. Right? The magnitudes multiplied together times the cosine of the angle between them. Right? A cross product, you multiply the perpendicular components between them. So that's important for like opening a door, like to turn it like toward. But we're not there yet. And so, okay, what's a pretty fundamental application of this that would definitely make sense? Right? So you guys know this box are the same thing. Right? Let's say you have a shopping cart that you're pushing across the floor. So got a floor, got a shopping cart, it's got some wheels, and I'm gonna draw for you guys a partial free body diagram. Okay. This is not gonna be a complete free body diagram. I'm gonna leave some stuff out, but just to draw the parts that are relevant. Suppose, see if you were pushing straight horizontal, now I'm not gonna draw it yet, but I'm just saying, for instance, if you're pushing straight horizontal, and as a result, this cart moves some distance, let's say d, some distance d as a result, then you just say, well, that pushing force times how far it goes, that's the energy transferred into it. And everything's parallel, so boom, boom, multiply, done. Okay. But what if you aren't pushing straight parallel to the floor? What if you're pushing kind of on this weird angle? You're kind of pushing down and forward at the same time. So you have a force that looks like this. Force is kind of down like that. Okay. We get a dashed reference line. So this dashed line is parallel to the floor, like the horizontal axis. Okay. Well, is the amount that you're pushing down to the floor actually moving that cart forward? No, there's nothing to do with that. Right? Only the forward part's actually doing anything, isn't it? Okay. Which might make you think, well, maybe we should split this force into components. Ooh, components. You guys remember some of the first stuff you learned in this class? I think the very first quiz I ever gave you guys was, hey, can you break stuff into components? Can you navigate your way around a triangle? I said that's going to keep coming back, and oh, here it is again. It keeps coming back. Okay. So here's the angle beneath the floor that you're pushing that cart. Okay. So now you guys see, let's label these components. What's this top one called? What times what? Force times cosine of the angle, because see how it's adjacent to that angle? Okay. Okay, so this one must be force times sine of the angle is how much you're pushing into the ground. Okay. But remember that the component that's parallel to the ground, well, that's the only part that's actually moving the cart, right? I mean, the vertical part isn't. Now, maybe you can make the case that the vertical component would cause the normal force to increase, which is true, which would also cause friction to increase, which is true, which would overall slow the cart down. Okay. So that would affect the motion of the cart, but let's leave that aside for now and just say the energy transfer from the person pushing on the cart. Okay. So the question is, how much energy was transferred That's to say, how much work was done on the cart. And you guys see that work is equal to, well, it would be the cosine component of the force, which would be F cosine theta, all multiplied by the distance that it goes as a result. And I bet you guys saw this by now anyway, but in case you didn't, just to bring this all full circle, you guys see you could just shuffle those around a little bit, and that would be exactly force times distance times cosine theta, which is the exact same thing as this right here, which is also the same thing as this dot product. Okay? So that's what that dot product of force and distance means. Okay? You guys good so far?
Wait, could I take a picture of that?
Yeah.
Okay.
All right. So next example, let's see if you guys get this one. Suppose you have a textbook. This textbook has a center of mass. Let's do a quick free body diagram on this. Say this textbook has a weight of, I'll even give you guys a number. Let's do 20 newtons, 20 Newton weight. Okay? And you're holding this textbook. You're just holding it at rest. Wouldn't there be a force from your hands? That would also be 20 newtons. Keep that in check. The dry diagram, just like that. Okay, so that's the free body diagram of the book. That's the forces on the book. One down, one up. 20 newtons down, 20 newtons up. Now, I said at rest, but if you only had that free body diagram, would you know if it was at rest? You could be moving, couldn't it? Actually, it could be moving in any direction, and that would still apply. Let's say that this book is already in motion. It's already in motion horizontally. And let's carry this book horizontally a distance of, 5 meters. Okay. So how much work was done on the book to move it 5 meters horizontally? Okay. So demonstrate got a book right here. Go hold it. Okay. So many newtons down, so many newtons up. Okay. I'm just moving it horizontally across the ground. Okay. What do you guys think the answer to this question is? Yeah. They're saying 0, right? 0 joules. 0 joules. There was no work done on the book. There was no energy transferred into it by moving it horizontally. Okay. Now, why would that be? Because the direction of the force and the direction of motion are perpendicular to each other. There is no parallel component. So in terms of that dot product, then everything just zeroes out. The cosine of 90 degrees is 0. Okay. Also, what this is consistent with, you guys remember this could be a free body diagram for an air hockey puck? And an air hockey puck might be in motion, and that would still be it. Maybe moving horizontally. You don't need a horizontal force to get it to move 5 meters. I mean, if it's already in motion, right? Maybe there was some initial force to get it to start moving in the first place, but once it's in motion. Right? Or how about Voyager spacecraft? Aren't there 0 forces at all on the Voyager spacecraft? You guys know that too. So to move it some distance, you don't actually need any energy as long as there's no force in that direction. So that's okay. But how about this though? What if, same book, same weight, 20 newtons. Let's say the same force from your hands holding it up, 20 newtons. But this time, we're going to take this book and we're going to move it upwards, a height of 5 meters. So how much work to lift the book 5 meters vertically? Now you guys will say, okay, well, work is force times distance, the dot product, right? And now the force and the distance are in the same direction. So 20 Newton force because we're applying 20 newtons. Right? What's applied here is we're moving up at constant velocity, right? But obviously from the free body diagram, FBD free body diagram, that would be the case because those forces are balanced. So we're moving up at constant velocity, applying a 20 Newton force to do that times 5 meters. You guys see that there's 100 joules of energy transferred into the book, moving upward. Is that? Okay. Which is going to lead to the next building block that I'm going to get to, the next mechanical energy formula. Because if you think about it, if you transferred you transferred 100 joules into the book to move it up 5 meters, that book now has 100 joules of energy associated with it by being elevated some height against a gravity field. I bet that would be called potential energy, wouldn't it? Potential energy. Okay. So let's look back at this this derivation here and say, I wonder if we could sort of figure out a formula for potential energy just from this. The applied force, wouldn't it just be equivalent to the weight? Right? I mean, that's where that came from. So mg for the weight of the book, right? You're applying a force opposite of that, but same magnitude. Right? And then some distance, but if it's against a gravity field, isn't that distance always some height value? That's why I call this h here. So wouldn't it just be mg times h? The amount of work that you put into the book to lift it would be mgh. Okay? And that's also the amount of energy that the book would have, potential energy from moving that height. Okay? You guys get that concept? This is exactly the next formula, mgh.
Did you show the first, the one before this?
Oh, yeah. Right. Yeah, oh yeah, see these side by side?
Yeah.
Right. So yeah, moving a book horizontally, there's no work associated with that, but moving it against a gravity field, there is, and then, okay. I should say too, moving it horizontally could be work as long as there would be a force in that direction, but there wasn't over here. Okay. All right, so next page. So gravitational potential energy. Now, a lot of times I just call this potential energy, but AP does distinguish between this type of potential energy and, well, spring potential energy, which we're about to talk about. Okay. Now, what's the variables for this? Okay. If you get some old handouts or something from another textbook, you might see PE. I used to use this. That's intuitive potential energy. Okay. But the problem with this is it's very easy to mix this up and think it's two variables multiplied together, which it does not. Okay. So what AP does is they just call it capital U or U sub G. Right? Right. Capital U is potential energy. U sub G is saying specifically gravitational potential energy. Okay. So in my recent notes, I've been trying to switch over to capital U. Okay. And this has a formula. And you guys already know the formula because, well, we sort of just derived it. It's just mgh. The energy associated with being elevated in some gravity field is mgh. Okay. M is mass, G is the gravity field, H is the height above, let's say ground level. Okay, something like that. Okay. So draw a picture for you guys, and then we'll dig into like exactly what and why and how this works. Okay. So take that textbook, just park it right on the edge of this table, right where it's like teetering on the edge. Okay. This book has some mass M, it's some height h above the floor, and it's in some gravity field G. Okay. Oh, height 0 right there, something like that. Okay. Okay, so great. If you know the mass, the gravity field, the height, multiply all of them together, and I guess you get what a unit of like some number of joules that represents the potential energy. Okay. Now remember what potential energy means. It's the energy that could potentially be recovered after it goes through some process. Like, what if you tip this book, you give a little tap, goes, crashes into the floor. Well, that crash, that impact with the floor, that's a good amount of energy, but where did that come from? Because I did tell you that energy was conserved, so that had to come from somewhere. You just didn't create it. And this is the interpretations that if you're doing energy counting, it's like, okay, well, it was elevated in a gravity field and it had some mass. They multiply it all together. Right? Okay, so when I was first going through physics, I was always like very carefully scrutinizing all the formulas. I was always looking for like, is there any kind of internal inconsistency in physics? Spoiler alert, there is not. But in case you're wondering, or maybe you had a similar thought process to what as I did when I was a student, this formula I did not buy right away. I had a question about this, and I was looking at that H, like that elevated height. Right? And here's the problem I had with that was, here, set this up right here. You guys see this textbook right on the edge of the table? It's pretty close to a meter off the floor, isn't it? Right, so you could do this mass times 9.8 meters per second squared times about 1 meter, get some number of joules. Great, all good, right? Except, what if I dug a hole right here? Okay. Isn't there a whole floor beneath us? And what if this book instead like fell through that floor and went like several meters down below? So it's not just a height drop of 1 meter. Now it's like what, like 4 or 5 meters, something like that. Okay. That would mean that the potential energy would be a completely different number. Not by touching the book or doing anything to the book, but just by digging a hole right there. Okay. All right. So how's that internally self-consistent? How does that work? Okay. And it turns out that that's okay, and I'll tell you guys why that's okay. Because if you define height 0 right here at this floor, so you're allowed to define height 0 before the ground level wherever you want, and as long as you're consistent within any problem, any setup, throughout the conservation of energy problem, then everything works out in terms of energy accounting. And falling through the floor, you would just say it falls into negative territory. So it would have like a negative height if it's like way down below this. And you could give that like a negative number of joules of energy, which maybe doesn't make a lot of intuitive sense, but in terms of energy accounting, in terms of the math, actually everything checks out perfectly fine. Right? Alternatively, you could take height 0 and just move it down several meters. So put the floor way down below. And what that would do is it would give the book a lot more potential energy, right, in terms of energy accounting. And then what if you went back and like filled in this hole, so or maybe dropped the book like a few feet to the left so that it like doesn't fall through the hole, it goes crash landing on the floor. Well, crash landing on the floor there, it would have potential energy above that new height 0 that was way down below. And then again, in terms of energy accounting, everything works out. So this does check out. You guys get that? Right. Next thing, well, let's do a couple of graphs because I want to talk about spring potential energy, but I'm going to use a graph to lead into this. Right. Let me split this paper in half here. Ooh, maybe I should go landscape with this. That's what I should do. Right. So I'm going to give you guys a couple of stories, and then we'll make a graphic that applies to either one of those. So either you push a cart with a constant force for some distance, or lift a textbook some height. Okay? If you're pushing in a distance, in a direction motion, or if you're lifting a textbook against gravity, either one of those, you could make a force versus distance graph that looks pretty similar. So we're doing force measured in newtons versus like some displacement measured in meters. Okay. And if that force is constant, can you guys draw what that graph would look like for a constant force? A constant force. Okay. Right. You guys have never seen this graph before, or well, not that I remember anyway. Okay. You guys have seen. Usually, time goes down on this horizontal axis, doesn't it? Right, for the graphs we've been doing. So this is distance. We've got force versus distance. Right? Constant force. Did you guys draw a graph that looks like this? Right. Basically that, right? Okay. Now, something else you guys know about graphs is that different properties of a graph could tell you different physical quantities. For example, a v versus t graph obviously could tell you the v velocity, but the slope of the v versus t tells you something about acceleration, and the area under the curve tells you something about displacement. And if you're ever not sure what information you can extract from a graph, then a good trick to do is to look at the units of the axes and say, what do I know about some property of a graph based on those units? For example, guess this rectangle right here? What are the units of the area of that rectangle? Newtons times meters, which is some number of joules, isn't it? So the area under this curve represents maybe some work done on the cart or the textbook, right? Or maybe the energy that either of those objects ends up with, right? Maybe the final potential energy of the textbook. I'm going to say the area of that rectangle represents the work done on some object. Hey, and that would just be force times distance, wouldn't it? Okay? Which is like the work equation that I gave you guys. Right? Now, why do I make a big deal about that? Because I want to give you guys a little bit different scenario that, I mean, if you get this, then this next part is going to make a lot more sense. Okay? Let's go back to springs. Suppose you got a block and you compress it into a spring. And as a result, you compress the spring some amount, I'll call X, something like that. And the spring has some stiffness, some spring constant, I'll call K. Okay? So K is the spring constant in newtons per meter, and X is the compression. How much you compress that spring, right? Or it could be stretch. You know, if you stretch a spring, then this would also work. You guys remember Hooke's law? Hooke's law says that the force to compress the spring is equal to kx. Some textbooks say negative kx. matter of perspective. So there. So let's make that graph. Because f equals kx, huh? Looks like we're juggling variables that look pretty similar to this graph that I just made over here. We got forces, we got distances. So let's throw compression distance x on the horizontal axis. That could be in like meters or centimeters. Okay? And force in newtons on the vertical axis. Well, you guys played around with springs, spring scales, and I have a spring right here. So the spring is ballpoint pin. If I push this cartridge into before I push it, right? Like right now, there's no force on the on the spring, and it's not compressed at all. Right? Compression is zero. Right? If I push this cartridge into it, right, it takes more and more force. The more force I apply, the more it gets squashed. Right? And hey, do you think the spring right now, spring loaded, has lots of energy stored in it, potential ready to go, and I can get all that energy back by releasing the cartridge, go pew, fly off. Wonder what the energy associated with a compressed spring is. That's what we're about to find out. Can you guys draw this graph? Maybe some of you guys have already drawn this graph. What's this graph look like? F equals kx, Hooke's law. F equals kx. It is a linear relationship. That's a direct relationship, isn't it? With the slope of k. Of course, an f versus x axis, set of axes, right? Okay. And you know what? Side by side, these are looking like a pretty similar story, aren't they? I mean, the one on the left is a constant force. Compressing a spring is a variable force. Right? But wouldn't the area underneath the curve also represent the energy stored in that object, in this case, a spring? Right? So this area, the area under the curve, is the energy stored in the spring. That area right there. Do you guys think that you could take some generic value x and some resulting force, which is equal to kx, and solve for the area of that triangle? Right? Let's do that. Do that right now. Okay, so the energy stored in that spring. Oh, they should just side by side. You guys can see this play out. That's called spring potential energy. So our next building block, our next mechanical energy. Okay? It's written as U sub S, so U is potential energy, but the subscript S is talking about a spring. Well, it's the area of that triangle, and that's 1/2 base height, because the area of the triangle is 1/2 base height. It has a base of some general value x, and a compression amount, or the force is equal to kx, because Hooke's law, that's Hooke's law right there. Hey, you could consolidate this, just bring the x's together. Isn't that 1/2 kx squared? There you go. So now you know Hooke's law, F equals kx. But now you know something else about a compressed spring, which is the energy stored in it, is that expression right there. Is that all right? Okay, and then the final main building block for mechanical energy is kinetic energy. Kinetic energy. Okay. This is the energy associated with motion. So I'll say energy of motion. If something's in motion, if it has some speed, it has some associated kinetic energy. Okay? Which, if you think about it, you guys remember that all velocities are relative. So how fast is anything ever moving? Well, it's got to be relative to something else. So, interestingly, maybe the amount of kinetic energy also might depend on your frame of reference. What's the character for this? If you see some old materials or from other books, you might see Ke, which I like because it's intuitive, Ke, kinetic energy. But again, you might, same problems before. It looks like two things multiply together, even though it doesn't. Okay. So AP just uses a capital K, and I've been switching over and using that too, depending on how old my materials are. Okay. Now, when you guys draw capital K, make sure that you can distinguish that from lowercase k. So capital K is kinetic energy, lowercase k refers to spring constant most of the time. Okay, so different things. Careful about that. Okay. Go ahead and give you guys the formula right now. And I'll show you maybe sort of where this comes from. So 1/2 mv squared. Okay. that's the expression for kinetic energy. Kinetic energy is, well, 1/2 times the mass of the object times its speed squared. And I'm saying speed because remember, energy is a scalar value, so the direction of the motion doesn't really matter. Okay. All right. Now, where does that expression come from? Well, I'll give you guys sort of 2 points of view. One is going to be a graph. I mean, yeah, what's the derivation of this? Took people a long time to figure this one out. I don't know if I have a really super awesome answer for you guys, but I'll give you 2 kind of mediocre answers, or two answers. Okay. One is this. Let's do a momentum versus velocity graph. Okay. Now, momentum we haven't even talked about yet, but I'll tell you guys, momentum is mass times velocity. Okay. And then, okay, well, velocity could just be that axis. Okay. Well, this graph just sort of definitionally has to be a direct relationship. So if someone's going twice as fast, then just multiply it by its mass, and that value is twice as much too. So direct relationship. Okay. And if you look at the units, this would be kilogram meter per second, which is also equivalent to Newton's time seconds. Okay. And of course, this axis is meters per second. Okay. The area underneath this curve also represents some number of joules. I forgot to say the slope of this line is m. Okay. But the area is some number of joules. And if you work out with variables, you get exactly this expression right here. It's the same thing. Area of that triangle is what's boxed up there. 1/2 mv squared. Okay. And the other perspective I can tell you guys for kinetic energy, which we're actually really close to. I'm about to do this pretty soon in the notes. Goes back to this Galileo problem of dropping stuff off the tower. Because you guys have a way to solve this already with those kinematic formulas. I'll show you guys that through energy accounting, you'll get the exact same answer. And if that's true, then that also confirms that kinetic energy must be this expression because it all is self-consistent. Okay. All right, guys ready to do a conservation of energy? Okay. All right. So yeah, something I mentioned before, but this is a hugely important concept in this class, is conservation of energy. Okay. Energy is conserved. You can't create or destroy energy or any number of joules. However many joules there are in a closed system. Now, a closed system means that there's no outside forces acting on it. Okay. You can have all kinds of crazy interactions within that system if you want, like things falling and spring in and move in, but the number of joules when you do energy accounting is always the same number of joules. Okay. Now, what you are allowed to do, what you can't do, you can't transfer from one energy type to another. Can't transfer, right? So conservation of energy, you can write like this. The sum of energy initial is equal to the sum of energy final. Okay. So within a closed system, might even think of maybe even like the whole Milky Way galaxy is basically a closed system. And then however much energy there's been, a billion years ago, it's the exact same amount of energy there is here. Also, read this, the sum of initial energy is equal to the sum of final energy. You guys are maybe kind of familiar with doing a process like this anyway, because back when we were doing kinematic stuff, we were always going from some initial point to some final point, some point A to some point B, the top of the tower to the bottom of the tower. So that part is still intact. Right? Actually, let's tackle that example right now. So let's go to Galileo's Leaning Tower Pisa. I guess he owns it now. And Galileo's dropping stuff off. And maybe we want to know, like, how fast is this stuff crash landing? What is the speed? Solve for that. Okay. All right. So, yeah. Okay. I'll do this new method right here. So the sum of energy initial equals the sum of energy final. Okay. Let's solve this in terms of variables and then plug in some numbers and So you guys the same thing. Oh, I have to give you guys a height change. Right. All went through some height change H. Okay. So at the top of the tower, when Galileo is holding this at rest, isn't it all potential energy? So I'll call it potential energy, initial. And when this ball is crash landing on the ground below, it definitely has energy motion, so there's some final kinetic energy. But the potential energy is now gone because it's at height 0, so if you define height 0 down here, then that would be the case, right? So this is very straightforward. Galileo's not throwing it, he's just dropping it. So potential at the top, kinetic at the bottom, but those must equate because of energy counting. Now you guys know potential energy, I told you guys earlier today, is mgh, and kinetic energy is 1/2 mv squared. So you know that. Oh, what's going to cancel on both sides?
Mass.
The mass, which was actually the whole point of that initial experiment, wasn't it? Right, was to show that mass doesn't matter. And you guys know that. So, okay, so that's consistent at least. Now, if you go solve for this V final, okay, then V final squared equals 2gh. So V final is the square root of 2gh. Okay, so that's the answer in terms of variables. Right? Let's do this. Let's compare that to what the answer would have been from your kinematic formulas, and also plug in some numbers and see how it all checks out. Okay. So the old way was V final squared equals V naught squared plus 2ax, isn't it? Here. Well, you actually had 3 kinematic formulas. Remember the third one, you could show system of equations for the first 2 to be the solution to those. Third one also doesn't say anything about time, so that's another reason I like that one. If Galileo drops this thing from rest, this number just goes to 0. Then, hey, wouldn't final velocity be the square root of 2ax? And look at this, side by side. Square root 2ax, square root 2gh. You guys do see that's the same thing, right? Because g is a type of a, and h is a type of x, right? Is that? As long as you drop it from rest. Right? You could even plug in some numbers. Let's do that real fast. Let's say that, well, call acceleration like 10 meters per second squared. And the height of the leaning tower piece is about 50 meters, so let's call it 50 meters. And final velocity would be from the old kinematic point of view. This is all kinematic. This is the old way of doing it. Be the square root of 2 times 10 times 50, that's 1,000 meters per second squared, all inside the root, okay, which is 31.6 meters per second. Okay. And the new way of doing it is going to be square root 2gh, but that's just the same thing. 2 times 10 meters per second squared, height drop of about 50 meters. So the boom, it's the same thing. If you like numbers. Okay. So here's through energy. Well, it's a solution from the page before, right? The square root 2gh you see all over the place in physics. I mean, obviously you've seen it before, you're seeing it now. Even if you had something like a water tower and there was like water spurting out the bottom of the water tower and you needed to hide the water tower off the ground, like how fast is the water spurting out? Oh, well, that also be square root 2gh. So you get to fluid mechanics, Bernoulli principle kind of stuff. So that's there too. Okay. Right. You guys good so far? All right, there's one more idea I'm gonna plant in you guys' minds before we take off today, which is I have to scroll back a few pages in the notes because sort of glossed over a detail. Well, maybe. You guys remember this potential energy is mgh? And it's like, okay, that's all fine and good. I mean, the work you do lifting it would be its weight times height, so it all checks out, seems to make sense. Okay. But take a look at that gravity field. Gravity field G. 9.8 meters per second squared. Isn't that really only true like at the surface of Earth? Right? And you guys remember from the last couple of weeks that once you either take off a rocket and get further away from the Earth, like inverse square law, G will decrease, right? Or for that matter, if you tunnel down inside the Earth, G also changes. So this G is only true locally, and so mgh, maybe that works for potential energy, but only over, say, distances near the surface of the planet. Right? What I'm trying to get at is that there's a more universal way to talk about potential energy. And this MGH is only a good approximation of that for like at the surface of the planet. So there's a universal gravitational potential energy. Right now, this one, because again, here's why. The whole U equals MGH, okay, G is localized. Okay, so this is why we're into industry. Okay. Now, I'll give you guys the formula right here. This one takes some deep thinking, and I'm gonna explain this tomorrow, but I'll just leave this with you guys for now. It's negative. It's negative G M M on R. Okay. I will tell you guys that negative G M M on R. What is this good for? Okay. Well, if you want to derive escape velocity, right, escape speed, I've promised you guys that I'll derive escape speed for you. You have to use some version of this. So if you're getting farther away from a planet, then that little g is going to change. So you have to use this. Okay. Now, if your radial distances are pretty close to each other, like let's say you're going from this R1 to this R2, or R2 to R1, either way, okay, where the height change is not that big compared to the radial size of the planet, okay, might be radial size of the planet, then this actually simplifies to approximately mgh over some height change h, right? Where h would be the difference of the two r's, like r1 and r2. So in this case, like h would be r2 minus r1. Right? This actually simplifies into this. Okay? So that's as far as I can get today, but tomorrow I'll tell you guys where this comes from, applications of it, how to get escape speed from this. Then I'll also talk about power measured in watts. Okay, so that's where we're going with the story tomorrow. Oh wait, this is, okay.